Okay, morning everybody. Okay, today we'll be going through another past year paper. Today, the paper I'm using is Presbyterian High School. Okay, last year prelim paper. Okay, so this is it's the same as before. Okay, if you have not got the paper, you can download it from my drive. It's the link to my drive is in the description bar below. Okay, you can click on it and get access to it. Okay, if you have done it, okay, I will be going through the questions. So if you need any particular question, okay, just scroll the video to the respective questions that you need. Now let's look at the paper. Okay, for this paper, okay, science physics paper, the answer for the MCQ is here. So if you have done it, you might want to pause the video here and check which are the questions that you have some problems or which questions you may have made some careless mistake. Then we'll go through the paper together. Okay, for question one, okay, for question one, it's a simple question, but it's one of the questions that we actually tend to overlook. Okay, as students, okay, we will always focus on like how to read a micrometer screw gauge, how to use a micrometer screw gauge, how to likewise for the same as how to read a vernier caliper, how to use a vernier caliper, ruler, etc., etc. But one of the things that we always forgot is we forgot what's the range for micrometer screw gauge. For example, like if I'm using a micrometer screw gauge, I'm looking at the measurements of less than 2.5 cm. Okay, so if I have anything less than 2.5 cm, let's say 2 cm stuff, I actually want to use a micrometer screw gauge because it will give me the best or the better accuracy as compared to what? As compared to your vernier caliper. Vernier caliper, the range of the instruments, okay, is in the textbook also, okay, is you range from 1 cm to roughly 12 cm to 15 cm. Okay, so it depends on what model of vernier caliper you have. So if you're looking at a meter rule, okay, of course a ruler, a meter rule of course will allow me to measure from 1 cm to 100 cm. So of course the difference between the various instruments is the accuracy. Okay, for vernier caliper, I can measure up to a decent accuracy of 2 dp in cm if I'm looking for measurements ranging from 1 cm to 12 cm. Anything more than that, I'm actually better off with using a ruler because it will give me a better accuracy. Okay, for likewise, if I'm looking for anything less than 1 cm, let's say maybe 1.5 cm, okay, instead of using a vernier caliper, I may want to consider using micrometer screw gauge, okay, because micrometer screw gauge has a range of maximum of 2.5 cm. So anything below 2.5 cm, its accuracy is much, much better than a vernier caliper. Okay, this in terms of range of the instruments, this section, okay, this area is where we tend to actually forgot, okay, when we do our revision. So as students, I will be actually primarily looking at how to use vernier caliper, how to solve zero error for vernier caliper, and likewise the same thing for micrometer screw gauge. And this is the section that I will actually forgot. Okay, I will actually forget to revise, okay, the range of the instruments that is needed. So when you do your revision, okay, remember to look at the range of the instruments, okay, that the instruments are actually best used for. Okay, so we have like stopwatch, vernier caliper, micrometer screw gauge, and even normal meter rule. Okay, so look at the range. Question 2 is a standard kinematics question whereby I drop the ball down vertically. Okay, and nothing much they say about friction, so I will assume it's ideal situation whereby friction is ignored. Okay, and after that, if no friction is in the question in this context, which means is dropping down in free fall, is with what we call a increasing velocity. So the acceleration experienced by the object will be actually 10 meter per second square, and I will say that the speed will be increasing indefinitely. Okay, so if you look at the object whereby, if you look at the questions whereby they ask for the greater speed, since this is ideal situation, so the greatest speed will be actually be L and M. Between L and M, the bottom layer, where the further I go, the faster the ball will become. Okay, so that will be the fastest speed between L and M. And of course, being the fastest speed, okay, with no air resistance in contact, so there's nothing to slow me down. So the time taken actually would be actually the fastest at the furthest away, further away. So the further away I am, the faster is my speed, and the shorter will be the time taken. So that's why my answer will be L and M and that will be option D. Okay, remember this context, the question look at is actually an ideal situation whereby there's no air resistance. If the other alternative for this type of question is maybe the question will factor in air resistance, and we will deal with it in like the context that we have will be with air resistance, we'll be looking at terminal velocity. So there will be a limit of the maximum speed that we are talking about. Because at terminal velocity, your velocity actually is the maximum, and actually it will actually stop there. The speed will not increase. Okay, but for this case, because it's ideal situation, your speed will actually increase indefinitely. So that's a slight difference between the two of them. Now for question three is a vector addition. Yeah, but it's just that instead of the usual forces, okay, now we are looking at velocity. Okay, remember, tip to tail or parallelogram, these two methods are used to add vector, not just forces. Okay, now we are looking at two velocity. One is pointing downwards. Okay, one is pointing to the right. Okay, it's on the boat. So I think the boat is missing. Okay, the boat will be here. Okay, so what's the resultant force acting on the boat itself? So if I redraw the diagram, the boat will be here. That's represented by the dot. Okay, so you will have a downward force, a downward velocity, which is V, and I will have a right side velocity, which is U. Okay, if you look at the parallelogram method, what we will do is we actually create, okay, the parallelogram, the two parallel lines, so that I can form a complete parallelogram. Then what I do is I will actually find the resultant force, or sorry, resultant velocity from the object all the way to the opposite end. Okay, so this will be the resultant velocity. Okay, so if I look at it in terms of parallelogram method, this will be my answer. Okay, so if I using tip to tail, okay, remember tip of one force. So the first force I'll be using, let's say if I use U, okay, will be pointing to the right. Tip of the force, okay, pointing to the tail of the second force. So the second force is V, will be pointing downwards. Okay, after that, what I do is from the starting point to the ending point, I will join it up. Okay, that will be the resultant force, as well resultant velocity. Okay, so if you use tip to tail, okay, this will be what your diagram look like. Okay, if you use a parallelogram, this is what the answer will look like. Okay, but both of them will give you the same answer. It's just different method of presenting the answer. So what we are looking at is we are looking at U pointing to the right side. Okay, we are looking at U pointing to the right side. We are looking at let's say we are looking at V pointing downwards. V pointing downwards. Okay, let's mark out V pointing downwards. V pointing downwards, V pointing downwards, V pointing downwards. Okay, U pointing to the right, U pointing to the right, U pointing to the right, U pointing to the right. Okay, and I will definitely know, take a look. The resultant velocity is pointing to the bottom right corner. Okay, bottom right corner, which is here. Okay, bottom right corner, which is here. So you look at it, the answer, there's only one answer only, which is C. And from there, I will be able to deduce my answer, which is C. Okay, so whether you use tip to tail method or parallelogram method, both method works. Again, both method essentially at O level, we are looking at vector, adding it vectorially. Okay, so for vector addition, both methods is as good as each other. But if you're looking at higher up, let's say you're looking at JC or Poly, you're looking at it as a vector additions, I will actually recommend method 2, tip to tail method, okay, for higher up. Okay, because higher up, if you look at higher level, the forces I'm dealing with, the addition the vectors that I'm adding is actually more than 2 vectors. Okay, it could be 3 or 4 vectors. So for adding of vectors, let's say 2 or more, let's say 2 or 3 vectors, 4 vectors, or even 7 vectors. If I'm adding all these vectors together, tip to tail method will be more efficient. Okay, but as of now, at O level, okay, whether it's tip to tail or parallelogram method, okay, both methods are equally as powerful. Okay. Now, question 4 is a slightly tricky question. Okay, question 4 here, the rectangular block given is 2 different material. 2 different material here. The clues that is given behind this statement is actually that both of them have different density. Okay, so because they are different material, so they will be definitely having different densities. Okay, and of course, measuring the mass. Okay, acceleration in which they are falling freely. Okay, I will not recommend this method. Okay, comparing the acceleration, okay, it could be they could be different sizes, or the question only talk about material, so they could actually be different sizes. So if I have flat surface, that one rectangular block is bigger, flatter, The other one will be like slightly slimmer or this thing. The resistance, the velocity, the velocity, the resistance might be different. So it is not a good way of comparing the mass. Comparing the length and breadth and height, what does this statement means? Okay, this statement, when I say I compare the length, breadth, height, this statement actually talking about is I'm actually trying to get the volume of the rectangle blocks. Now, if you talk about volume, you talk about density, you bring us to the formula. Density is, okay, mass over volume. Okay, and in fact, the question asks for measuring mass. Okay, and true enough, okay, if you look at volume doesn't help us to compare the masses because both of them have different density. So if I have different density, if I have different volume, I will not know what is the masses of the, I will not be able to deduce the masses. Okay, it doesn't mean the one with the bigger volume will have a bigger mass, or does it mean that a smaller volume will mean the smaller mass? Okay, it actually depends on the density also. So it will not be a good comparison. Okay, by knowing the volume. The other one is we hang the spring, we compare the extension. Okay, some cases here we will talk it as like, maybe we refer it to measuring the weight of the object. Usually we look at extension, we look at the weight of the object, the forces of the object. But in this case, the forces, if we hang it on the spring, the forces we are talking about is actually the weight of the object. And weight, we have a formula which is mass times G, gravity, okay, gravitational field strength. And the best thing about this is that gravity for both blocks is on the same planet, so they will actually be the same gravity. They will be under the influence of same gravitational field strength. And because of that, I will be able to know that the one with a higher weight, or what we call a higher extension, a bigger extension, okay, will infer or will imply that the mass of the object will actually be higher. Okay, so the bigger the mass, the bigger the extension. So if you compare the extension, it will actually indirectly tell me the size of the mass. So the block with the higher mass will definitely have a higher extension. So actually, if you look at the extension, I can actually infer the mass of the object. Okay, and likewise for question number 4. Number 4 is a classic example of beam balance, whereby I compare the mass on the right side and left side. So definitely 4 will be a good way to compare the mass. So if 3 and 4 does allow me to do what the question asks, and with that, you give me the answer C, okay, which is the answer for this particular question. So look at how the questions needs the student to actually employ different methods of using density, weights, volume, all these things. Okay, this is like a combination of your chapter 4 mass, weight, density. Question 5, I will not dwell too much. It's a simple calculation whereby we look at the student's ability to apply the formula. Density is mass over volume, and at your level, I don't think you will have a problem using the formula, because if the area is given straight away. Okay, so area, volume, okay, all this will be what we call a basic arithmetic. Now, question 6. Question 6 is a classic example of two-force system. Okay, the weight is on the object is held by the force in the tension. Okay, so that's denoted by T, and the force that is acting on the block is what we call the weight of the object. So since the question says stationary, okay, I love this word stationary. Stationary implies what? Not moving. It implies A equal to acceleration is 0 meter per second square. And this means if I apply Newton's law on the object, F net equal ma, okay, I will definitely know the right side. The A is 0, means the right side of the equation is a big fat 0. And what are the net force? Net force means the sum of forces on the system. It will be tension minus the weight. Okay, and it will give me the tension, and the weight will be of the same value. In this case, the weight of the object, remember, our weight of the object is not 20 kg. Weight is Newton. So weight mass m times g, which is 20 kg. Make sure it's in kg. Multiply by 10 Newton per kg, the gravitational field strength, you will get 1200 Newton. Okay, so I will know that, okay, the weight is 200 Newton. Indirectly, I'm also saying the tension in the rope is actually 200 Newton, which is answer D. Okay, Newton's law. Okay, and the standard formula of weight equal to mg. Okay. Now this question 6. Now question 7. Question 7 is the turning effect. Okay, it's I would say it's a simple question of mass. Moments equal to force times perpendicular distance. Okay, I will not dwell too much on this because I would deem that this is quite straightforward lah. Okay, so if you have any problem regarding this question, just let me know. Okay, to identify the moments here. Question 8. Okay, which of the question 8 vertical lift vertically, which of the example will have the greatest power? Okay, greatest power. Okay, power, the classic example, the standard formula that we have is energy divided by time. Okay, energy divided by time. So what we are saying that if I want the power to be big, okay, I want the power to be big, my numerator have to be a bigger value, my denominator have to be a smaller value. Okay, so which means I will need to have actually to look at the energy and the time taken for the object. And true enough, the questions, when we talk about the question says lift vertically. Vertically, one of the hints that we tell you that the energy we are looking at, if you leave it vertically up, okay, is what we call potential energy, which is controlled by the formula mg vertical height h. Okay, time, okay, straightforward, is time lah. Measure in seconds. Okay, so let's take a look. So if I want the power to be big, remember, power to be big, my time definitely has to be small. Okay, so smaller time, same time possible, shorter time definitely much better. Okay, longer time is out. So option you are left with C and D first. Okay, now, so you look at the C and D. See, shorter time, same time does not mean it is long or short. It just means it's possible answer, I would say. Okay, that same time that doesn't give me enough information to emulate the option yet. So after the question says, shorter distance. Okay, remember, the vertical height, which is mgh is controlled by vertical height. Okay, so the bigger my height is, the bigger is my potential energy. So the height I need has to be big. So shorter distance, definitely not the answer I'm looking out for. So if C is out, only left with D. So D will be the best answer in this case here. So for a constant value, so shorter time will definitely means the power of the motor is getting bigger. Okay, surface of the kettle is hot. Metal surface. Okay, metal surface is hot. What happened to the cool air outside? Cool air outside the kettle when it come in contact with the hot kettle. Okay, cold air. Okay, cool air means we are talking about hot, cold air outside. Normally we look at density. Why we look at density? Because cold and hot that will bring us to one concept called convection current. And when we look at convection current, we definitely be looking at density change. Okay, density change, hot rise, cold sink. Okay, and less dense will rise. Okay, cold air being denser, you will sink. Okay, so that's why we look at the context. Air will rise, hot air rise, density has to decrease. Okay, hot air rise because it's less dense. Okay, so likewise, if it's cold air sink, means it has to be denser. Okay, so if you look at the particular setting here, okay, there isn't much about the cold air, so there's only this answer B, which is correct one. Okay, so definitely B will have to be my answer. Okay, so straightforward regarding density changes. Okay, MCQ so far, I would say there's only 2 or 3 quite interesting question. The rest should be, I would say, is a standard open net, standard safety net question. So students should be looking at least until question 9, you'll be looking at around 7 marks or 9 marks. Okay, so let's proceed on. Okay, hot air is sealed inside metal can. Hot air is sealed inside metal can. Okay, there's a vacuum. The can is in the vacuum in outer space. Okay, hot air cool down, hot water cool down. Okay, space. Vacuum. The moment it's a vacuum, we talk about cooling down. Now, vacuum. Okay, cooling down, you conduct, convect, radiation. There are 3 methods, and among these 3 methods, conduction, only radiation can take place in a vacuum. Conduction and convection will be stopped immediately, because it's a vacuum, no particle there. So conduction, so no need to cross. So which means conduct is out already, conduction is out, convection is out. So this two matter is out because it's vacuum. So the moment you see conduction, you see conduction is out straight away. Okay, so now we look at the context. Okay, now how does it escape, okay, into space? Okay, so I'm looking at radiation. Okay, I'm looking at radiation. Okay, I'm looking at radiation. So if I look at radiation, you'll find evaporation doesn't take place. Evaporation, I will definitely need molecules, so definitely will be out also. Okay, so now in this context, you find all the A, B, C, D, all the answers are not are wrong in this case. So what has gone wrong? Okay, for this question here is you have to read the questions carefully. Okay, in question 10, the question says that the water is sealed inside the metal can. So the hot water is in the metal can here. Okay, so for it to escape, okay, the heat must travel through the tin first, must travel through the can, reach the surface of the can. Then after that, the heat will be lost through radiation. So which means before radiation take place, one of the method must occur, which is conduction. Okay, conduction must occur. How? Because the heat from the water, the heat must conduct through the tin itself. Okay, through the layer of tin, through the tin surface, through the can surfaces, okay, through the metal surfaces, from the inside tin, from inside of the can to the outside, the exterior of the can. Okay, before heat can be radiated out from the can. So in this case, you will find that B is actually my answer, even though we say that conduction cannot take place outside, okay, the can, but within the can, conduction is still possible, because there is still a medium, which is the molecule itself. Okay, so in this case, because of the question, the way the question is crafted, okay, you'll find that actually B is actually the correct answer. In this case, the question is asking the question is how the heat actually travel from the water through the tin and to the space. Okay, so there's a two-step heat transfer that we are looking at, not just a simple straightforward from the tin to the space there. Okay, so students, you have to be alert on the type of questions or how the question is being crafted. Now, question 11. Okay, question 11 talk about evaporation. Okay, after that, so take note evaporations. Okay, temperature changes. Okay, so the moment you talk about evaporation, the moment I have evaporation, the temperature changes. This change, I think students, you should know, when you have evaporation, you have what we call cooling effect occurring. So the temperature actually will reduce. So straight away you will know, because I say evaporation, you know the temperature of the object actually will decrease. So straight away you will know that, okay, the temperature of the liquid will actually be decreasing. Okay, and of course, we should know, okay, evaporation only from where? Evaporation should only take place, occur on the surface of the liquid only. Okay, boiling occur everywhere in the liquid, but evaporation only occur at the top layer of the surface. So that's why answer I know straight away is B already. Okay, so that's why we have to be alert to the various clues that's given in the question so that we can solve the question fast. Ultrasound. Okay, ultrasound. Okay, from the muscle to the bone. Okay, ultrasound is sound is longitudinal wave. Here you must remember longitudinal wave. Okay, for sound, okay, is travel the fastest in where? Fastest in the denser medium. Fastest in solid, or what you call denser medium. Slowest in gas. The less dense it is, the slower it gets. Okay, so when I travel from muscle to bone, muscle to bone is definitely much denser. So bone being denser, when I travel from muscle from less dense to denser, the speed of the object actually will increase. The speed of the sound will actually be increased. So it will be less dense to dense. So which means the speed of the ultrasound will actually be increasing. Okay, so when speed of the ultrasound increase, okay, what causes it to increase? Using the wave formula V equal F lambda. Okay, if the speed increase, okay, take note, remember, when speed increase, the frequency does not increase. Frequency is like the identification number. It's like the identity of the frequency of the wave itself. If it still remains as ultrasound, after traveling from muscle to bone, it is still ultrasound, which means the frequency of that wave actually remains the same because its identity is remaining the same. It's still ultrasound. So you will have the same frequency. And if the speed increase, frequency remain constant, the only guy that is affected is actually what we call the wavelength. So the wavelength of the ultrasound actually increases, okay, when it travels from muscle to bones, denser medium. Because of that, the speed of the ultrasound actually increase. So the option for number 12 is actually D. Okay, so take note of the reasoning. Remember, for sound wave, for waves, remember when you are traveling through the wave, despite different medium, okay, you'll find that the frequency of the wave actually remains the same, because for sound, for longitudinal wave, your frequency is like the identity of the wave itself. If the wave remains the same, its identity, its frequency actually remains the same. Eclipse of the sun. Okay, eclipse. Okay, the sun, when the moon come into the earth and sun. Okay, so you see you have sun and earth on extreme end, the moon is in the middle. So the moment the moon is in the middle, you block out all the sun already. All the sun, you will block out all the rays, okay, coming from the sun. So in this case, you will find that the only option available will be infrared, ultraviolet, and visible light. Remember, infrared, ultraviolet, visible light, gamma ray, X-ray, they are all called EM wave. Okay, but they all belongs to what we call your EM wave. They all belongs to the EM spectrum. They all belongs to the same what we call your transverse wave. So they are all in the package one. So it's not possible that I can actually filter out visible light, ultraviolet, infrared rays, just without any instruments. Okay, so as a result, all the ray, once the moon blocks the ray from the sun, all the waves in the EM spectrum will actually be completely disappear for that moment. Okay, so that's why answer is B. Okay, I cannot filter out any of the rays, okay, without any instruments. Remember. Now, question 14 is transverse wave. I would say it's an interesting question, okay, because we always see a standard question to say, hey, please define transverse wave. Transverse wave, particle move perpendicularly to the wave motion. Is quite a boring question. But in this case, for this question, it actually give a nice twist to the question, okay, whereby it call for a pictorial representation of the definitions. Okay, when the question says that the cork is on the water surface, and when transverse wave travel from X to Y. So in this case, the question talk about the wave motion is from X to Y, okay, right side, okay, from left to right, okay, and as a result, the cork will move. The cork here will actually behave like a water molecule, okay, so which means as the water wave move up and down, okay, as the water wave move from left to right, you'll find that all the wave particle will actually be moving up and down. Okay, why up and down is because the question state, or you should know, actually water wave or ripple waves, okay, are actually transverse wave. And when it travel from left to right, my wave molecule actually move perpendicularly to the motion, which only means up and down. So that's what we mean by the particle actually vibrates about its fixed position. The only thing it does is only going up and down. Okay, so this is what we mean by the definition of transverse wave, but in picture form. Okay, which is what makes this question quite interesting. 15 is reflection on echolocation. Okay, how far is it from the bottom of the boat? Okay, how far below the bottom of the boat is the shore, or aka how far is the fish away from the boat? Remember, when you talk about echo, okay, remember echo is whereby the sound travel down and it travel up. So there is what we call a distance travel is actually 2 times. So there's a 2D involved. Okay, so take note, okay, and the sound reach from the boat again after 1.2 seconds. So the time taken is actually, let me change the color. So the time taken for boat to from the boat down and go up again is actually 1 turn. Okay, so actually time is actually 1.2 seconds. So actually 1.2 seconds is the time taken for the sound to travel from the boat down to the fish and up again to the boat again. So there is actually a complete cycle, I would say. So speed, okay, for sound is a constant. So it's distance by time. Okay, so the speed is 1005. Time taken is 1.2 seconds. Pardon me, is 1.2 seconds. And remember the distance here we're referring to is 2D. Okay, it's go and come back. So there's actually 2 directions involved. Okay, so take note of the direction. Okay, so there's 2 directions. Notice that there's 2D. Okay, if you look at the mathematics, okay, I want to find D. Okay, you'll be able to locate the answer to be, let's see how much. Let me get my calculator. 1500 times 1.2 divided by 2. It will be 900 meters straight away. Okay, and it will be option B. Okay. So take note of the 2D, the distance, and take note of the time. Okay, so nothing complicated here. Just be careful of the mathematics. Okay, common tricks that we always use for echolocation is whether the time is a full up and down, or the distance is a 2D, or these things. So take note of the common tricks that we use. Question 16 is electrostatics. Okay, after rubbing, the same strips are actually further away. So take a look, they are further away. Okay, and we know that the only time that they cause these two strips to be moving further away is whereby you have what we call repulsion force. And for it to be repulsion force, it means where light charge must exist, because light charge repel, so this charge must be the same. Okay, so that's why I would say this question is quite easily done. Okay, but it is a good twist to it. Okay, same thing, because it's really represented in terms of picture. Okay, it's not what we always see. Okay, whereby it's just light charge attract, light charge repel, and light charge attracts. Okay, but this time round, the question actually, the setter actually used a picture way, a pictogram to actually represent the keywords. Okay, cell is 1.5. Okay, this one I will not dwell too much. The standard definitions. Okay, so definition. Okay, students, please know what they are. Okay, it should be in the textbook or is in your notes. Which two changes to a metal wire both increase the resistance? Both increase resistance. Okay, so you have to take note of, we are looking at the formula. Resistance is rho L over A. Remember, rho here refer to the density, the resistivity, the type of material. I want the resistance to increase. So basically, I need the material to change, okay, to a higher resistivity. I need the length to increase, and I definitely need the diameter, okay, diameter to actually decrease, okay, a thinner cable. Okay, so what we are looking for is a thinner, longer, maybe a different material. Okay. Now, so let's take a look. So if I decrease the length, no, I cannot do it. Okay, if I increase, yes, possible. Increase, yes. Decrease thickness, yes. Okay, then increase thickness out. Okay, so I'm only left with B and C. B and C as a possible answer. So what about increased temperature and decreased temperature? Okay. Okay, so only left with temperature here. So what do I mean by increased temperature? Here we need to employ some of the basic concept that we learned in your primary school. Why increased temperature is the one that I need? Because why? When I increase temperature means I'm making the wire hotter. What happens when things become hot? Okay, the first instinct that we know, when things become hot, okay, the object actually expands. Okay, when I expand for wire, when it expands, aka it means the length of the wire actually increases a bit, but it does increase. Okay, so likewise, okay, when I hit the wire, the temperature increases, it expands, the length increases. Okay, and when the length increases with the decrease in thickness, definitely the resistance will increase. Okay, so take note of the slight inference that the marker actually requires the students to know. Okay, whereby temperature and expansion, he bring in the expansion section. Okay, so take note of it and how we link it to length. Okay. Now for question 19, ammeter, voltmeter, same thing. I will not dwell too much. It's a classic example. Voltmeter has to be in parallel arrangement. Ammeter has to be in series to measure the current correctly. So I believe students, you will know which is the correct arrangement. So I will not dwell too much on this. Okay, question 20. Question 20. Remember, we talk about safety feature, fuse. Okay, fuse, the moment we talk about fuse, there are few things that we always like to highlight to students. For fuse, okay, the moment we talk about fuse, few things that we need to take note is, we will require the students to know what are the possible ratings. Okay, because in terms of fuse rating in the market available, it's not like any number I can find. In the market has actually a standard set of values that there is that's customized to the fuse itself. So students, you will need to know what are the set of values. And then followed by the keywords. Okay, the keywords to actually describe or actually to write about the usage of the fuse. Okay, so students, you need to know what are the keywords needed when you describe the function, how the fuse function, or how does the fuse save the appliances and the user itself. So these are one main keywords. And the last one is to know the location. Okay, when we use a fuse switch, okay, we have to make sure that the fuse is actually planted at the right place, aka what we call your live wire. Okay, so the location of where you place the fuse actually affects the effectiveness of it as a safety feature. Okay, so fuse, there are these three sections that we always encourage the students to take note. Okay, so after that, the last segment here is the calculation. Okay, current is 10 amp. Fuse rating is the cable attached to the heater is rated 15 amp. Okay, so what are the fuse rating that's given? Okay, so the current is rated 15 amp, but it doesn't matter because the fuse rating depends on the working current of the cable, and the working current given is 10 amp. Okay, so 10 amp, the next best reading, the next highest reading I'm looking at is actually 13 amp fuse. So I should actually choose a 30 amp fuse. Okay, remember the rating. Rating tell us, rating is with respect to the working current. Okay, so if the current is 4 amp, okay, even though the cable is rated as 15 amp, I still need to choose, let's say 5 amp for my fuse rating, the next higher rating. Okay, so take note of what we mean by your fuse rating, what we mean by fuses, what we mean by safety precautions, safety feature. Okay, so this is where we finish your chapter, your paper 1. Okay, then we will move on to your paper 2. Okay, so in the paper 2, what we are doing, remember to take note of the keywords and the thinking process of solving the questions. Okay, because the thinking process is more important than getting the correct answer. Okay, so this is where we look at how much you have done for your revisions and what are the gaps that you have in your revision, so that we can actually patch that gaps or patch that openings. Okay, so let's look at question 1. Now, question 1 is on forces. Okay, now you have two forces acting on the car itself. Okay, driving force. Okay, and resistance force. Okay, now how can you tell whether the object is accelerating? Okay, with two forces and accelerating, the first instinct that we have would be Newton's law, F net equal ma. And of course, when we talk about acceleration, we will definitely have to talk about the net force acting on the object. And just nice, okay, there are two forces that's looking at the system. One is the driving force, which is 950, and there is a resistance force, okay, which is 550. Okay, so the sum of forces or the net forces that we have will actually determine the magnitude of the acceleration here. Okay, so true enough, okay, we are looking at, okay, the net force as the answer. How do we tell the object is, the car is accelerating? Because why? There is a resultant force. Okay, because resultant force actually dictates, okay, actually indicates that there is an acceleration on the object itself. And of course, you can calculate the number. Okay, and that's what the question is asking you to do. Okay, you calculate the acceleration. Okay, one way of looking at acceleration in this case is to look at net force. After that, with mass, you can actually calculate the acceleration. But then for this question, you student, you have to take note that the mass of the car is not given, so you can't calculate at the acceleration using the Newton's law. But what happened is the question actually gives you the initial speed and the final speed. Okay, the initial speed and final speed. And of course, you can use acceleration formula, change in velocity, divide by time. Okay, take note, okay, this has to be final velocity, okay, minus the initial velocity. And true enough, you substitute the value, you get the answer straight away. Okay, nothing complicated. Okay, now what happened is when I apply the brake, okay, what happened? Describe how the horizontal forces change when the driver now applies the brake. Okay, now when I increase the brake, okay, when I apply the brake, okay, the forces, the opposing force will actually decreases. Okay, the opposing force will actually decreases. Okay, so one of the most obvious things is we will tell you when the braking force increase, the opposing force will actually be increasing. So what happened is the opposing force, the braking force will increase. Okay, when I jam the brake, what happened is the acceleration, the car will also be, the driving force will also be reducing. Okay, because of the resulting resistance force. So the moment I jam the brake, okay, the car will actually start to slow down. And when I slow down with the braking force, okay, it also means that the air resistance of the object, of the car experiencing, will also be reducing. Because when I reduce when I increase my braking force, okay, the engine force, the applied force will actually be reduced. So this driving force on the car will actually be reduced. So which means the driving force will reduce, and or what we call eventually the net force of the object will also be reducing. And because I'm already jamming at my brake, I already apply my brakes, the velocity of the car will actually be reduced. And when the car reduces, when the speed of the car reduces, the air resistance will also reduce. Okay, because we're going at a slower speed, the air resistance experienced by the car will also be reducing. So these are what happened to the forces that is experienced by the car itself. Now, for question 2 is regarding like what the questions mentioned is about pressure and density. Okay, pressure. When we talk about pressure, okay, pressure, the first thing we look at is if you look at the formula, if you look at calculation, it will be pressure will be force divided by perpendicular area. Keywords that we always like to use is we like to use the word perpendicular area. Okay. Now, so we have the weight of 6 meters squared, and there's a weight is 0.072. Here, take note, a simple trick that we always use. This is weight of each metal. So we are looking at a total weight of 0.072 times 6. Contact area, the pressure exerted is 0.820. This is stacked together. So the area we are in contact, this is the area that we are looking at. Okay, the bottom surface. Okay, so the total force we have is total weight multiplied by 6 divided by the pressure. You will get, okay, the area that's required. The formula is substitute here. You will get the area. A lot of zeros, but I think it's quite fairly straightforward. Now, what happened is when I, instead of stacking up, I actually spread out the area. So originally, when I stack up, okay, when I stack up, like what I did in part A, okay, the area that we are looking at is at the bottom surface here. This is the area. This area, based on the calculation, is 0.00527 meters square. Okay, so now what happens when I actually distribute these 6 pieces out, okay, in the space, okay, on the floor? What happens is you find that now instead of 1 area, I actually got 6 area. Okay, so you'll find that my perpendicular area, okay, actually increase by 6 times. Okay, and because my perpendicular area actually increases, okay, you'll find that my pressure actually decreases. Okay, so if you look at the explanation, it's quite straightforward, whereby I increase the area, then after that my pressure decreases. But what I actually will encourage the students to take note is that whenever we write, okay, whenever we explain pressure, we always try to use the keywords like contact area. We always try to don't just use contact area. We just want to be precise. What area we are looking at? We are looking at the perpendicular contact area. So I always like to encourage students to write the word perpendicular, okay, to tell the marker which area we are using, what area are we looking at. Okay, so I want to be more precise, so I like to use the word perpendicular contact area. Okay, and after that, deduce about the pressure. So sometimes I will also say, like, if I want to be more precise, I will actually write my I will always craft my answer in this 3-step process. I always talk about the forces that act on this that is involved in the question. I'll talk about the perpendicular area, and I'll talk about the pressure. For example, I will say that since the weight remains the same, okay, since there is the same weight throughout, okay, then after that, what I do is I would mention that the perpendicular contact area increase by 6 times. So look at how I craft the question. Oh, by 6 times. Okay, then so what I did now is I actually talk about the force. I talk about the contact area. Why do I want to do this way? Because the formula also got mentioned these 2 factors. Okay, because pressure depends on these 2 factors. So I will want to use my formula. I always use the formula to actually guide my explanation. After that, what I do is before I talk about pressure, I want to highlight to the marker that I know what is pressure. So I will just insert a statement to say, since pressure is force per unit area. It's a bit long, but I would say that it's more precise. So that the marker know that I know the pressure is force divided by area. So it's force per unit area. Okay, to know that I know that it's divided by area, not times area, not plus area. So it's force divided by area, force per unit area. So I would like to use the word force per unit area. Then after that, I conclude that the pressure will reduce. Okay, so when I craft my pressure answer, I always tell students that I instead of like just writing area, perpendicular area, I always like to craft it in a systematic way. So I always do it in such a way that is actually I will use the formula to guide me. So I always talk about the pressure. I will talk about the force first. I will talk about the perpendicular area. Then after that, I'll conclude about the pressure using the correct keywords that I mentioned. Okay, perpendicular contact area, force per unit area, all these things. Okay, so these are the keywords that I always tell my students to actually you write to reinforce my understanding or my revisions, or even to tell the marker that you actually know what are the concepts involved. Okay, then after that, what I did here is for the next question is explained by spreading out. Okay, does it affect the density? Okay, so here same thing, density is mass per unit volume, all this. Okay, so there's the basic formula that most of us should know, mass over volume. Okay, you'll find that by spreading out or by stacking up, it doesn't affect density. Okay, because why? Because the mass and the volume actually remains the same. There's nothing changed except maybe the locations. Okay, so as a result, the density of the object actually remains the same. Okay. Now for question 3, it will be an interesting question. Okay, question 3 is a question pertaining for moments, but it has two pivoting point. Okay, which is what we call the A and B. So pivot A and pivot B. Okay. Now calculate the force X. Okay, so same thing. What we have is we're looking at the clockwise and anti-clockwise moments. Okay. Now, so if I want to look at force X, so I will take moment about A. Okay, so in this case, it will be moments about A. Okay, I would say taking pivot at A. Okay, so I will take pivot at A. So if I look at 620, the force 620, with respect to A, this will be my perpendicular distance. This will be D620, perpendicular distance for 620 Newton. And the moments I'm looking out for with respect to pivot A for 620 Newton, it will be a clockwise moment. So I'll label this as M620. So what happened is, why do I want to take moment at A? Okay, because if I take moment at A, I will be able to calculate the moment due to force X. Because force X with respect to pivot A, it will be an anti-clockwise moment, Mx. Okay, with the perpendicular distance from the force to the pivot here. So this will be the perpendicular distance X, which is actually 1.4 plus 0.6, which is 2 meter. Okay, so this will be 2 meter here. Okay, so true enough. Okay, so since the beam, everything is balanced, so I will say the clockwise moments will be equal to the anti-clockwise moment. So the clockwise moment will be the M620. So this will be M620. So it will be force times distance, perpendicular distance. So it will be 620 multiplied by 1.4, which is here. Then followed by what we call the anti-clockwise moment, which is Mx, which is force times distance. Okay, so given the distance is 2 meters, the force is X. That's what you're trying to find. You'll be able to calculate the magnitude for the force, which is 430. So what we are looking at here is we're looking at we're using the principle of moments, the clockwise and anti-clockwise, but it's about pivot A. It's about pivot A. So now what happened is at part B is that the guy is moving to the left. Okay, this guy is moving to the left. Okay, guy is moving to the left, but what has not changed is still the same. I have a weight here, which is 620 Newton. I have an X here, which is still here. Okay, and for force X, you'll find that for force X, okay, the perpendicular distance is still here. Okay, if I take pivot A. Okay, so here will be still 2 meters. What actually changes okay, is that as the guy move towards the A, move towards left, okay, you'll find that the perpendicular distance for 620, okay, as the guy moved towards the left, the perpendicular distance for 620 actually decreases. Okay, now for 620, for this guy, right, okay, there is, like we mentioned in part A, right, there is a clockwise movement, which is M620. Okay, so this is what's happening. And same thing for with respect to part A, okay, pivot A, X has a anti-clockwise moment, which we denote it as MX. That's what we have in the part A. The only thing that is different between part A and part B is that actually that the perpendicular distance for the guy 620 is instead of 1.4 meter, but now because I'm moving more towards A, you'll find that the perpendicular distance is actually decreasing. So how does it affect the magnitude of force X? Okay, so let's look at it. Now, for the entire movement, okay, while the guy is moving to the left, you'll find that the concept still remains the same. Your anti-clockwise movement still must be balanced with the your clockwise movement must balance with the anti-clockwise movement. Nothing changed. Or what should I say? Your MX moment MX, okay, must be balanced with your M620. These two will always remain the same because the whole beam is balanced. And true enough, okay, if you look deeper at M620, okay, moment by your guy, by the man, it will be the weight of the man, which is 620 Newton, multiplied by the perpendicular distance of the man. Mx will be the force X, multiplied by the perpendicular distance X. Okay, this is what we mean by the for the equation. So this is the X, which is 2 meters. Now, as the guy moves towards the left, you will find that, like I mentioned before, you will find that, okay, D620 actually decreases. This number actually decreases. Okay, the rest 620, the weight of the guy it actually remains the same. As the guy moves to the left, the weight still remains the same. It doesn't slim down or get any fatter. So the guy actually remains the same. So the weight actually remains constant. Okay, so if you look at these two numbers, if you look at these two factors, you'll find that while the guy moves towards the left, what we are seeing is that the anti-clockwise, the clockwise moment, M260, okay, M620 is actually getting, the moment by the guy is actually getting smaller and smaller. Okay, the clockwise moment is actually decreasing. And because the clockwise moment is decreasing due to the decreasing perpendicular distance, the anti-clockwise moment, mx, okay, because they are balanced, so it must also be decreasing to match the moment, the clockwise moment. So the anti-clockwise moment must also be reducing to match the clockwise moment. And when we say mx is decreasing, you'll find that for mx to be decreasing, only one factor has to change, which is your fx. My fx must be reducing, must be decreasing. Why mx decreasing, but why not the distance x? Because the perpendicular distance for the perpendicular distance dx, this distance is fixed. Okay, because your pivot A and pivot B is fixed at the location, your force X is fixed at the location. So the distance, so the perpendicular distance dx is actually remaining constant. It's actually unchanged. So for me to reduce, for mx to be reducing with perpendicular distance remaining the same, my force X has to reduce. So which means that I can actually see that as the guy moves towards the left, my force X actually reduce. Okay, and true enough, you look at the answer, okay, it's actually following the math. The math and keywords actually closely linked together. Okay, because the math and the keywords, they actually guide each other. So if I look at the perspective, if I look at the keywords, okay, I need to tell the marker, okay, what happened to the clockwise movement, what happened to the anti-clockwise movement. Okay, so I need to tell the marker what happened to the clockwise movement. And from there, I have to make reference to what happened to the perpendicular distance, D620. And I will also from there make reference to what happened to the force X, Fx. So these are the keywords that I should be writing, okay, in my answer. These are the 4 keywords that I should be writing. And true enough, you look at the answer, Okay, okay, these are the four keywords that will actually appear. So you look at math and keywords and explanation, they are not like separate from each other. Okay, they are actually reinforcing each other. They actually try to they actually guide each other in your answering of the question. Okay, so this is where I actually encourage students to actually take note of the keywords and actually draw references or make references to the calculations. Okay, because they are actually complementary each other. They are not two different concepts. Okay, explanation and calculation, they are not two different things altogether. They are actually the same. Question 4, the energy conservations. Okay, conservation of energy when the electrolytic is running, okay, from figure 4.1 to 4.2 is running towards the pole, I think pole valve thing, okay. So what happens is when it runs, okay, from figure 4.1 to figure 4.2, okay, what happened to the changes as you run faster, as you go higher in height, okay, as they both bend due to elastic energy. So I would say it's quite straightforward. I will not dwell too much. Okay, so as it clears the pole and clear the bar, so it will after it come down again. Okay, so it will be at the highest point. Yeah. So now when we look at the question, same thing from maximum height, yeah, or what we call highest point. Okay. Same thing. The explanation is quite. It's a standard high point to low point, so it will be a standard change in conservation of energy for EP to EK. Yeah, but what I want to highlight for this question is that, okay, when we talk about highest point, okay, some things that we need to take note is highest point, we actually refer to maximum height, okay, and we also refer it to zero speed. Okay, maximum height refer, it will be a maximum EP, potential energy, gravitational potential energy will be max. And at the highest point, it also means that it has, at the instant it will be momentarily at rest. It will mean that the EK will actually be what we call a minimum, or what we call EK0. So these are the things meaning clues that hidden behind that particular word maximum height. Okay, true enough, and it also means there's also one thing is that the acceleration acting on the object at the highest height is only what we call your gravitational field strength. So it will be G equal to A, which is 10 meter per second square. Okay, so these are the clues that we always like to tell students that is hidden behind the word maximum height or highest point. Okay, so take note of it. Okay, you may need it in other questions. Okay, but it's not this question. Okay, but you may need this information maybe in other questions, other questions that you encounter in the future. For question 5, electromagnetic wave. Okay, how frequency of the EM wave in vacuum differ with increasing wavelength. Okay, this one is quite straightforward, whereby you look at the wave formula V equal F lambda. The EM wave in vacuum, they all have the same speed. One of the property common number that you must remember, 3 times 10 to the power 8 meter per second. Okay, higher frequency, lower wavelength. It's an inverse relationship. Microwave is to use to heat up the food. NIM and spectrum to heat up the food. Definitely, you need to know the users for EM spectrum, all the waves, the arrangement of the wave, microwave, radio wave, gamma ray, infrared radiations, ultraviolet, visible light. You need to know the users. You need to know the wavelength. You need to know the arrangements. Okay, so take note of the users. Now, microwave here is application. Okay, or microwave is used to detect aeroplane. Okay, now the keyword I would say is like a large rotating area. Okay, it's actually rotating 360. Okay, now explain why microwave is used to find, how the microwave is used to find distance of aeroplane. Where in this what I call, in these particular instances, this microwave beam or this devices, it acts like similarly to like the ship echolocation, whereby actually the wave is actually emitted from the area, the antenna. After that, the moment it hits the airplane, it will actually bounce back to the antenna. And what you do is when the antenna, the computers will actually calculate the difference in time, okay, the time traveler, and given the constant speed, the bouncing back time, or the reflecting time, I'll be able to calculate the distance between the airplane and the area, just like echolocation. And from there, I will able to detect how fast how far the airplane is from the antenna and how fast the airplane is traveling. Okay, so this is what we mean by echolocation. But now this echolocation actually uses EM spectrum. Okay, then after that, suggest why it's important for the area to rotate a full cycle every 2 seconds. Every 2 seconds. Okay, it has to be 2 seconds. Why? Because we are looking at airplane. In echolocation, we are looking at fishes. They usually swim quite I would say quite slow as compared to aeroplane. So there isn't a speed limit of how fast my echolocation, my ultrasound has to be emitted from my emitter from my devices. But for airplane, when looking at airplane, because they are traveling very fast, okay, and because they are traveling very fast, they actually cover a lot of distance. So that's why my antenna has to be swinging around at a very fast speed. Okay, almost like 2 seconds, like what the question mentioned, 2 seconds for one full circle, so that I can actually detect the changes in speed, the changes in airplanes. Okay, and also airplanes also travel in different directions. Okay, so it's important for me to go 360 round, okay, in a short time, so that I can actually detect any planes that's coming to me at any location, any direction to be exact. Okay, so that's why if you look at microwave, you'll find that actually this is one of the reasons why, because I have to swing around 360 in a short time. I have to detect and the plane is going very fast. And that's why I actually can't use ultrasound. Okay, I have to use microwave, EM wave. Because why? Because if I use ultrasound, the speed I'm looking at is maybe like 350 meter per second only. Okay, it's actually quite slow if you compare to, let's say, microwave. If you travel in microwave, you look at in air, it's actually traveling 3 times 10 to the power 8 meter per second. So the speed is essentially like at least 4 times, or no, 4 times. It's at least 1,000 times, or actually 3,000 a thousand times. I would say it's 1,000 times, 1,000 times faster than the ultrasound. So whatever ultrasound can do, I can actually do it in 1,000 times faster. So that's why I actually need microwave instead of using ultrasound, okay, longitudinal wave as my echolocation. Okay, so that's one reason why we actually use microwave, okay, to detect airplanes. Sound, okay. Question 5 is EM wave, transverse wave. Question 6 will be on longitudinal. Okay, longitudinal audible range. This number we have to remember, 20 hertz to 20 kilohertz. Okay, nothing much. Okay, oscilloscope. Okay, obtain the speed. Okay, so this is the wave that's given to me. Okay, this is the wave that's given. So what we do is he obtain the trace on the oscilloscope. Okay, draw a trace that is quieter and double the frequency. Okay, same thing, double the frequency. It means that, okay, this is the original one. Okay, same thing as before, like I mentioned in my previous paper, when we talk about sound, when we talk about pitch, when we talk about quiet, loudness, okay, we are talking about the loudness of the sound. It has to deal with my amplitude of the wave. If I look at frequency, it will deal with my pitch of the sound. Okay, it will deal with my frequency. Okay, so the louder is the sound, the louder is the amplitude. So if I have loud sound, I will be looking at a larger amplitude, and vice versa. And same thing for pitch. If I have a high pitch, I'm actually looking at a high frequency. Okay, so if I have a quiet sound, this will mean this is a soft sound, okay, or aka smaller amplitude. Okay, double the frequency is like what I mentioned, double the frequency, or what we call is a higher pitch. And one thing that we see when we look at frequency, although we know pitch and frequency are packed together, but when we look at the wave itself, we actually don't see frequency that directly. We actually see what we call period. Okay, the period, the time for one cycle. This is the period of the wave. Okay, so when we say frequency, remember frequency and period is an inverse relationship. Higher the period, shorter the smaller the frequency. So if I have a larger frequency now, if the frequency increases, what happens to my period? My period will actually be decreasing. So if I'm looking at double frequency, I'm actually looking at half the periods. So actually what I'm looking at is that the wave actually becomes shorter. Okay, half of it to be exact. Okay, so that's why my original frequency was here. This is my original. My new frequency is actually, my new period is actually here. Exactly half of it. Okay, so exactly half of it. 4 square, original, 2 square is the new one. So that's what we mean by double the frequency, or what we call half the period. Okay, it's straightforward here, so take note of it. Lenses. Okay, lenses, like I mentioned before in my other paper, lenses, remember there are the ray drawing diagram, there's only 3 rays that you can draw. Okay, then from there you actually deduce, this 3 will allow us to deduce the location of the image. And the 3 rays, if you have forgotten about it, okay, the 3 rays, I have actually made a video on the ray diagram. Okay, I will put it on the link below to let you take a look again. But if you have forgotten, okay, you can refer to that particular video to see how to draw ray diagrams. Okay, so now same thing, draw 2 rays. Okay, now draw 2 rays, I'll go through together. So let's say for 2 rays, the first ray, like I mentioned before, you always draw the ray, what you call the ray 1. Okay, always from the object down to the optical center of the lens itself. Okay, so that's the first ray that I draw. Ooh, okay, remember arrowhead represent light ray. Okay, then what I do is second ray, it will be, I will choose ray 2. It will be parallel to the, I can't do parallel. It will be parallel to the object. Hits the ray. After that, what it does, it will cut the focal point. It will cut the focal point. Okay, it will cut the focal point. Oopsie. Let me go out a bit. Okay. You will cut the focal point. You will go straight through. After I remember, I need the ray. I need the arrowhead. And true enough, this is where you end like halfway. I would say halfway, not complete yet. But you will actually know the answer. Remember, for all light ray, you actually know the answer beforehand. Okay, for this case, you will find that the object distance, okay, is actually less than the focal length. Okay, it's less than the focal length, which means ultimately I actually know already this image, the image that produced is actually a virtual ray. It's a virtual image, and it's actually being magnified and it's actually on the same side as the object. So what we have here is we don't end the ray here. What we did is we also need to extend the ray back, okay, to form the image. Where's the ruler? Okay, let me get the ruler first. Okay, so what I do is I need to extend the ray back, and it has to be dotted line. Okay, then after that, what I do is I do the same for the other ray. Okay, I extend back. Okay, and I will know that this is where, and the intersection point is where the object will be. Okay, and remember it's a virtual object, so it has to be dotted line also. Okay, so it has to be dotted line. Okay, and whenever it's dotted line, okay, it has to be for this type of ray, this type of object, you know, it's virtual, it's enlarged, and always behind the object itself. So these are the characteristics that you have. Okay, and label it I, and this is what we mean by the ray diagram. Okay, and same thing. So what we do now is I have the arrangement now. I have a new arrangement now. Now the object, okay, they move further away. Okay, so now this object is actually, this object distance is actually more than 2f. Okay, it's actually more than f. Sorry, it's less than 2f. Okay. Okay, it's more than f, less than 2f. So I will actually know what is the characteristic of the image itself. And same thing, where do I find it? Is in the, it's in the textbook, whereby there are 6 possible scenario, possible location of the objects, and in that 6 picture, actually give you, they actually give you the location of the image, the characteristic of the image, the the uses of the particle lenses, the uses of particle lenses, and what are the properties of the image itself. So students, you have to be well versed in all the 6 images. And if you have done that, okay, you'll find that this answer is actually straightforward. You'll know what are the image, what is the answer that is, what is the answer that is expected from this arrangement, even though you have not drawn any diagram, any ray diagram. Okay, because the answer is actually predicted already. It's already prefixed. Question 8 is on electrostatic. Okay, so here what we have is a common situation whereby we pump petrol. When you pump the petrol, you find that there's actually static build up. Okay, because when the petrol actually run out from the delivery pipe, okay, there's actually friction between the liquid. And because there's friction, there will be actually charges involved. There will be some will be losing charge, and the other party will be gaining charges. So you'll find that there will be a charging up, there will be an accumulation of charges, okay, near the petrol tank and actually the delivery pipe. And that's one of the reasons why actually sometimes it's actually quite dangerous at the petrol when you're pumping petrol, because the build-up in charges actually cause sparks or explosion. Okay, because when we talk about earthing, okay, when your negative charges flow, okay, the moment charge flow is actually what we know as current, and this is what we call a spark. And with the petrol fluid fumes, you find that it catch fire easily and they will cause explosion. So one of the common characteristics that we always do is we actually like to earth the petrol tank, or we even earth the delivery pipe. Okay, so we actually provide earthing so that we can actually discharge the charges. Okay, we can actually earth the charges, we earth the tank to discharge the excess build of the charges. Okay, so that we can actually prevent all the sparks, all the sparks from forming. Okay, so that's what we do in the petrol kiosk, whereby you find that most of the petrol delivery pipe are actually earth to prevent all the charges from build up. Even the petrol tank is also earth. Okay, so now we look at another application whereby actually we look at funneling some of the coffee grains. Okay, you'll find that coffee grains, when I run through the funnel, okay, when the grains are actually in the funnel, okay, because of the motion they are running down and they are squeezing together, you'll find that there will be some friction, there will be some rubbing along the way. And because of the rubbing along the neck of the funnel, there will be some rubbing, there will be some friction occurring. So when it rubs, you will find that there will be some charges being deposited, or some electrons being lost or being gained. Okay, and most of the time you find that when the grains actually run through the funnel, the tip of the funnel, okay, the grains actually are being charged up because of friction. There will be some of them will be losing electrons, then some of them will be gaining electrons, and as a result, you will find that the grains, okay, they will actually be charged. Okay, based on the question, they actually gains a charge. Okay, they actually gains electrons. It could be from the neighboring charges, or it could be along the way. Okay, the charges from another coffee grain, it get passed on to the neighboring particle grains. But because of that, you'll find that the grains are actually charged up. Okay, of the same magnitude or of the same sign. Okay, you'll find that what we have is we call same charge, or what we call light charge occurring. Okay, your light charge occurring, and because they are light charge, the grain will actually be repelled. But of course, this is a good way, because when they are repelled, you find that because of the repulsion, you find that the grain are actually being thrown far away, where they are able to occupy different areas of the container, so they will not be all stuck up in the middle. So because they are being repelled, they are able to spread out in the container, so I can actually fill up the container quite evenly in this case. Question 9. Question 9, I would say is a fairly straightforward question, whereby it's a series circuit, whereby your 12 volts, okay, your current passing through the arrangements, okay, the series circuit, the current will pass through 150 ohms and 200 ohms components. Okay, so I will not dwell too much on 9A, because I would say it's quite fairly simple. Okay, it's a basic question that all students have to take note. Okay, so if you need explanation for this particular question, just let me know. Just drop me an email or drop me a comment in the comment bar below, and I'll get back to you ASAP. Okay, so question 9, I would say is quite quite a straightforward question. Okay, and question 10, section B, question 10, same thing I mentioned all my papers. You have to answer 2 questions. Choose the correct question. Okay, don't just do the first question or do the last question. Okay, aiming that or on the pretext that the first or last question should be the easy question. It doesn't work this way. Right? Okay, read the 3 questions carefully first. After that, decide on the question that you are more confident in solving, in getting the marks. Okay, then after that, choose that 2 questions. Okay, so the first question, it talk about air resistance. Okay, it could be on forces, on dynamics. Okay, so the roof is curved this way. Okay, it's curved this way. It's what we call your what I call your aerodynamics. Okay, it's made more curved. Why? Okay, it's because of to reduce the drag force. So whenever the curve, it actually help to part the air away, help to divert the air, okay, up to the rooftop so that it can reduce the drag or it can reduce the air resistance faced by the car. Okay, and because I reduce the air resistance, what I do, it actually reduce my petrol consumption. Okay, it actually make so it actually make my journey more efficient. So I will actually use my petrol more efficiently. Now the lorry is up the hill at a constant speed. Okay, so the lorry is here. The weight of the lorry is 180 kilo Newton. Okay, so it will go all the way up here. Okay, what's the work done against gravity? Okay, work done against gravity. Yeah, against gravity means I'm looking at actually the potential, this gravitational potential energy, or what we call the. If you look at work done, it will be distance. Okay, in the same axis as the force. Since the force is 180, which is pointing vertically downwards. Okay, the distance that is in the same direction as the force, it has to be the 7 meter. Okay, both are in the vertical axis. So it'll be a simple force times d parallel. Okay, and you get an answer straight away. Okay, or sometimes we will tend to say the work done with gravity is also known as gravitational potential energy. Where gravitational potential energy, which is controlled by the formula mgh. In this case, mg is weight. Weight is given already. Okay, which is 180 kilonewton. Then after that, the height, which is 17 Newton, which is here. So you still get back the same answer. So that sometimes we also say work done against gravity is also known as gravitational field strength. Gravitational is also known as gravitational potential energy. Okay. Now it takes 8 seconds to go up. Okay, up the hill, calculate the power, useful power. Okay, I would say straightforward. Power, okay, is energy divided by time. Energy given is in part A, time is 8 seconds. Remember, it's 8 seconds has to be SI unit. After that, you get the power straight away. Now, for the last part of the question here, it has a velocity time graph. And okay, so velocity time graph, the moment you see velocity time graph, we have to be alert. So to the 2 concepts that we're looking at, example, the gradient of the velocity time graph will give me accelerations. Okay. And the area under the graph will give me the distance traveled by the object. So these are the 2 concepts that we always use when we look at velocity time graph. And true enough, the question actually asks for this stuff, this value. So the lorry accelerate and travel at constant speed. So the acceleration during the first 6 seconds, or aka the gradient of the graph. Okay, so first 6 seconds we are looking at is here. Okay, so you're looking at the gradient of the curve. Or sometimes we are looking at, like, we look at the formula, it will be the final. This is the final speed. This is the initial speed. Okay, so if you look at the number, this will be the final minus the initial divided by the time taken. Okay, you will get the acceleration. It's quite a straightforward question. After that, the question will ask for the distance travel in the 8 seconds. Distance travel 8 seconds, you refer to the area under the graph in 8 seconds. So it will mean this trapezium. Okay, or what we call, it could be depends on what formula you like to use. Okay, I always like to divide it into triangles and rectangle. So it will be this case. So it consists of a triangle. It will consist of maybe a rectangle. and a thicker rectangle here. Okay, so this will form the complete shape of the area under the graph, which will also give us the distance of the travel. Okay, so it will be 2 times 1.48. Okay, so it depends on the shape that you're looking at. So this will be the triangle. Okay, so this will be, let me see. Yep. So this will be the slim rectangle. This will be the broader triangle. Rectangle. Okay, so these are the shapes that are involved. So once you have the shapes, the area, you look for the area, and that will give us the total distance that's needed, that's required by the question. And after that, okay, we move on to the slightly, I would say this is the last question, which is quite straightforward. Okay, the pressure. Okay, keyword here is, okay, six tires. Okay, I want the area of all the 6 tires. Okay, the area of each of the tires. Okay, so pressure will be force divided by area. Okay, 6 tire. Okay, so the area I'm looking at will be 6 tire here. So the pressure will be the weight of the lorry. Area here I'm looking at is actually 6 times area of the tire. Okay, so there's a 6 here. The area, the pressure is given. Okay, now take note, pressure of each tire here. Remember, each tire, pressure is the ratio. So for each tire here, pressure is, so it's a ratio of the force and area. So each tire, whether it's one tire or the whole 6 tire or the entire lorry, for pressure wise, always the same. So pressure on each tire, pressure on the car, pressure on the 6 tires. Okay, the pressure is always the same, but it's the ratio. Okay, so this will be 240 kilopascal. Area 6. Okay, because I'm looking at the total weight. So I need to look at the total tire also. So with this formula in mind, if you rearrange the algebra, you'll get the tire, the area of the tire that you need. Okay, the area of the tire of single tire. Okay, which is here, and you get at it as 0.125. Okay, here I would like to highlight to students that remember, do not multiply the pressure by 6. Although you say each tire, okay, whether it's 1 tire or 6 tire, the pressure is all the same because it's the ratio between the force and the area. So if I want pressure of each tire, it will be the force of 1 tire versus divided by the area of the 1 tire. If I want the pressure of if I want to use the whole weight, the total weight, I'll have to use the total tire. But regardless of whether I use weight of 1 tire divided by area of 1 tire, okay, this ratio and this ratio, they all end up to be the same number, which is 240 kilopascal. Okay, because pressure is the ratio between the weight and the force and the area in contact. Okay, so they are always the same. They are always the same number. So take note of it. For question 11, okay, question 11 on lenses is an interesting question where we talk about ray drawing diagram. Okay, so we have the ray AB CDE. This is what is given to us. Okay, and we have a right angle prism. Okay, here take note, the question requires you to measure. We literally need a protractor. So that's why when we always tell students that when we look for paper 1 and paper 2, no matter what's the situation, please bring a protractor, bring at least 2 ruler. Okay, why you need 2 ruler? Because in case you need to use parallelogram method for vector addition, you need to do some sliding. So you can actually bring 2 ruler and a protractor, because sometimes we actually require you to measure the angle itself, like in this case. So you measure the angle of incidence at G. So where is the angle of incidence? This is the angle of incidence, okay, at G, and the angle of refraction at G here. Okay, then after that, angle of refraction at D. Okay, angle of refraction at D will be here. This is the normal angle of refraction at D. It will be here. Okay, so this is the angle of refraction I'm looking at. Angle of incidence I'm looking at based on the question. These are the 2 numbers. So you take your protractor, you measure it directly, you get answer. It happens to be the same number, 45 degrees. Okay, so take a look at, so just take note that you need to bring a protractor. Remember, what happened to the light ray at C? Okay, at C, what actually happens? Okay, at C, let's take a look. Okay, at C, okay, the light ray actually incident on the surface point C. Okay, it did not exit the prism. Okay, it did not exit the prism and bend or refract away from the normal. It did not do that. Okay, why? Okay, here you take note, because this is what we mean by your total internal reflection. Because your total internal reflection is that when the ray is traveling from where? When the ray is traveling from dense to less dense medium. That's the first condition. Okay, and it happens that the angle of incidence at the surface is actually larger than your optical center. Okay, it's larger than your critical angle. Okay, so when you have these two conditions, first condition, it has to travel from dense to less dense. Okay, second condition, it has to be, the angle of incidence has to be larger than critical angle. When these two conditions met, the total internal reflection will occur. And so instead of the ray, instead of exiting at point C, you actually do a U-turn. You actually not U-turn, you actually do a bounce off. Okay, you bounce out. Okay, your internal reflect, you go to the other surfaces. Okay, that's what happened to be that's what happened to the light ray at point C. Okay, because your total internal reflection actually occur. Okay, now same thing for 11.1. Okay, complete the light ray F and G. Yeah, so same thing. So let me erase the thing. The answer is actually here, actually quite small. You may not be able to see it. Okay, so same thing. Okay, so you'll find that, okay, one interesting thing is that this diagram requires you to use a protractor to measure. You'll find that this two ray is actually parallel rays. So when I hit the surfaces at G, this angle I and the angle I at surfaces B, they are actually the same number. So which means whatever angle that's refracted at B, this angle refraction, okay, will actually be the same number, will actually have the same value as at G. Okay, so let's say, let me call a ruler first. Okay, so this ray, whatever ray at G, the refracted ray at G, okay, it will actually have the same angle. Oh, my ruler hang already. Okay, give me a minute. Yeah, I can't rotate the ruler. Okay, so let's say I do away with the ruler. So it will actually have the same angle as this ray here. This angle here, RG. Okay, your RB will be the same value as RG. Why? Because both of them have the same incident angle. Okay, because these two ray F and ray A, they are actually parallel rays. So they will actually hit the prism at the same angle. So you measure the same angle, you bounce it off, you end up here. After that, you'll be same angle, same angle, same thing, you'll be the same incident angle at point C. You'll be the same angle at you'll be the same angle at point I. So at angle IC and I would say F lah. Let's say, okay, IZ maybe IY. Okay, so IY, both of them will be the same angle. Okay, same thing. The reflected internal reflection will occur also. Okay, and because of that, it will bounce off at the same angle here. Everything will remain the same. Okay, it will be refracted at the same angle here at E. Okay, so you'll find that for the ray F, okay, it actually follow the same path as what's given. Okay, it's just that it's just being slightly displaced upwards or displaced to the right. So you'll find that the ray that you draw, okay, will actually have the same angle, will actually travel the same angle as the given ray by the question. It's just that it's being displaced to the right. Okay, so that's what I mean by the new ray that you're supposed to draw. The only thing that you have to take note is for this drawing, you have to use the protractor, you have to use ruler to draw the rays at the exact angles. Okay, after that, one use of the right angle prism, okay, a periscope. Okay, so it can be any other, it can be a periscope, it can be another, yeah, it can be other users also. Periscope, periscope, or it can be a periscope is the easiest, I would say, is the one that comes to my mind. Then after it can be a digital camera. Inside a digital camera, it does happen. We use lens also. Okay. Now, question 12, I would say, is the most interesting question among this paper. Okay, it's among a few papers that I see. It has very, very, what I call it's not new, right? It's an application that we don't really see often. Okay. It's quite interesting. Okay. Now, for the polar bear, okay, we have a polar bear, okay, and we have a thermal image of the polar bear. Okay, and this polar bear, and based on the question, is that the dark color represent low temperature. Okay, so which means the sky here will be low, temperature will be low. Okay, this will be low. Okay, the snow will be high. Okay, so based on information for this question about the temperature of the object, so you can take a look because of the hint that's given to us. Okay, dark color means lower temperature, so darker is a lower temperature. So in this case, you will know that actually the fur and the snow will be at the same temperature because they are the same color. Okay, the brighter color will be the brighter color will be hotter. So in this case, the reverse, the dark color, the sky will be actually be the coldest. So I would say this question A is actually quite straightforward. The question actually, the marker actually give us some clues to guide us really. Now the polar bear consists of short hair and long hair. Okay, that's interesting. Okay, the long hair are hollow. That's even interesting. Okay, and it contain air. Okay, now explain why is how the fur actually reduce the amount of air lost by the polar bear. Now here the keyword here is air. Okay, of course the hair is also one of them lah. But definitely we know that hair, air, all these are bad insulators. Are bad conductors. They are good insulators, and because of that, okay, the air actually act as a thermal insulations for the polar bear, and as a result, the polar bear it will actually help to reduce heat loss to the environment via conduction, poor conductions. The other way that we look at is also other than the material itself. Okay, the fact that how they are arranged, the short and long hair. So you have maybe a short hair, a long hair, a short hair, and a long hair. So the arrangement of these the short and long hairs, okay, it actually help to reduce. It actually help to reduce the amount of convection current that can occur within the fur itself. Because with long hair and the short hair, long fur that's covering the short fur, you'll find that actually convection current, the hot air cannot rise that effectively. Okay, so once hot air cannot rise, cold air cannot sink, you literally may help to actually minimize convection current happening at the surface. And when you have reduced convection current in this case, it will actually means the heat loss is actually much reduced. So in this case, you look at this question, it's a simple statement: short hair, long hair, hollow, and air. Okay, so this statement has four things in these two statements has actually four hints trying to tell has hints to trying to tell us what are the modes of heat transfer that has been used. Okay, so long and short hair, the arrangement of it will actually tell us things about convection current. Hollow and air, we talk about conductions. Okay, so these are the two modes that we have. And of course, the question means that the fur is white. It's a white fur here. Okay, polar bear has white fur. So the color white is also a color when we talk about emitter, we talk about white fur, we talk about radiation. So the whole questions actually sum up the transfer of heat, the three modes of heat, very effectively, very elegantly. Okay, three statements, and you actually got all the mode of transfer inside really. Okay, so it's actually quite an interesting question. Okay, quite a good question. Okay, then after that, the next part we look at is actually the black skin, okay, white fur. Okay, that's interesting. Okay, now, so what happened is that explain how the heat is being retained by the polar bear. Okay, same thing, black and white. Okay, it tells about the emitter, white being a poor emitter, black being a good absorber of the thermal radiations. So this one I would say is quite straightforward. Now, the second image that we look at is about the daytime. The same image, but it's taken at daytime, and it uses ultraviolet radiation. And the question already hint to us to say that okay, the brighter image, the brighter indicate large amount of ultraviolet. Okay, and based on the questions, there's an outline, all these things, and you find that the polar bear and the sky is actually is dark in color. This is actually the sky. Okay, just for info. Okay, and this is actually the ground, the snow lah, basically. Okay, so based on the picture, okay, the question below actually depends a lot on the clue given. Okay, excuse me. So compare the absorption and emission of ultraviolet by the objects. Same thing, because of the hint given, large amount UV means the brighter it is. So you'll find that the snow, okay, snow is very bright, it's white in color, it's very bright. So it will actually, okay, indicates large amount of ultraviolet on the snow surface, which means the snow actually doesn't absorb any ultraviolet. We actually absorb minimal ultraviolets, okay, because it's being the brightest. And the reverse will happen, okay, bright color, based on the question, bright color indicate large amount of ultraviolet. So the absence of ultraviolet will be indicated by a dark patch. So likewise, the sky and the polar bear actually absorbs the UV rays, okay. So these are ultraviolet. Okay, so these are what are hints that's given from the pictures. Okay, and it allows us to actually answer the question. So now one of the interesting fact that we say that the sky is black, even though the sun actually emits the ultraviolet. So the sun come from the ultraviolet come from the sun, it hits the sky. But yet you find that the sky is not lit up. The sky is not full of ultraviolet. Because based on the question, the sky is black. Okay, so it's not full of ultraviolet. What happened is because it's black, based on the question, because it's black, it means that the ultraviolet is actually being absorbed by the sky. Okay, so when ultraviolet upon entering the earth, okay, actually the clouds actually absorb all the UV ray. And this is one of the important facts of the sky and the clouds. They absorb all the UV light, so that when sun ray actually hits the surfaces of the earth, where it hits the surfaces of human beings, okay, we will not be overexposed to ultraviolet, and we will not be causing skin cancer. Okay, imagine the sky, we are sky, okay, we are the clouds to absorb all these UV rays. All the UV ray will blast down to the surface of the earth or the man at full blast. Okay, you find we will be roasting really. Okay, because we have too much ultraviolet really. Okay, and we are not experiencing it because the sky up there is actually absorbing all the UV rays. The last part that we're looking at, okay, is the hollow part of the fur. Hollow part of the fur is actually transparent tube filled with air. Okay, and it acts like optical fiber. Okay, optical fiber. Okay, with the word you see optical fiber, one thing that comes straight to my mind is we could be talking about internal reflection, the bouncing away of light ray inside the optical fiber. Okay, when we talk about light ray bouncing off, okay, transferring, okay, data, okay, from one end to the other end. Okay, then after that, the question also talk about the fact that the ultraviolet does not reach the polar bear skin. Does not. Okay, so what happened? Why doesn't the ultraviolet radiation get passed to the skin? Okay, based on the question, okay, you'll find that when we talk about ultraviolet, we talk about optical fiber, and we talk about it doesn't reaches the skin. When you put these two together, when I talk about optical fiber, but then it doesn't work, the ray doesn't enter, it doesn't end up at the surfaces, you will actually tell me that these two things, you actually tell me that total internal reflection does not occur. Okay, it acts like optical fiber, but the phenomenon does not occur. The ray doesn't get directed to the surfaces, to the skin. So it means that although it act like optical fiber, but it does not have the condition for optical fiber to occur. And true enough, okay, you'll know that, okay, for optical fiber to occur, okay, the transfer medium here, we're looking at the optical fiber, for this to be internally reflected, okay, you'll find that the condition for internal reflection to occur, it has to be traveling from dense to less dense, less dense medium, okay, and the angle of incidence has to be larger than the critical angle. So these two conditions must exist first before internal reflection can occur. Okay, so for the fur here, you'll find that when the ultraviolet enter the surfaces here, these surfaces is actually air. Okay, so these surfaces is actually your fur, okay, or your hair. Okay, and you'll find that air will actually be a less dense medium because it's a gas. So it will be a less dense medium. Fur, which is a solid, fur will be a denser medium. So if you look at the light ray actually travel from less dense to a dense medium. if you look at the light ray, ultraviolet is traveling, it actually travels from a least dense medium to a dense medium. And when it travels from the least dense to dense medium, this first thing is the direction. It actually doesn't allow total internal reflection to occur. Because total internal reflection to occur, the light ray must enter from dense to less dense. It must be traveling from dense to less dense. So the medium is the type of medium, the transfer direction of the transfer actually is wrong already. It's different already. So because the direction of travel is actually different, as a result, your total internal reflection here will not occur at all. This is one of the main reasons why total internal reflection don't occur, because the direction of travel is actually wrong already. Okay, so that's why total internal reflection does not occur. The other possible reason that radiation don't pass down to the skin is because when the light ray actually hits the hair, the light ray may actually, the ultraviolet hits the hair, the ultraviolet may actually be absorbed by the ultraviolet, the hair already. So between the ultraviolet is actually absorbed by the hair, and as a result, none of the ultraviolet actually hits the skin, the polar bear skin. Okay, and this is it could be one of the reasons why ultraviolet actually is being absorbed, okay, in the hair and not absorbed at the polar bear skin area. Okay, so these are some of the various possible reasons that we can actually come up with, and some of these reasons are actually embedded in the question itself. Okay, so we have to really read the question carefully. Okay, because sometimes like what this question does is actually the marker actually embedded some clues or some hints, okay, to help us in our answering. Okay, so with that, this will be the last question for your section B. Okay, same thing as I mentioned before. Okay, remember to choose your section B question carefully. Okay, because section B question is 10 marks each. So choosing the right question will actually value add your results quite substantially. Okay, so with that, okay, this will be the end of this paper. Okay, the next paper, I will be going through a few more paper. It could some of it will be the normal CAP paper. So if you like to see, like to get notified by the videos, okay, if you're interested in the video, okay, same thing, subscribe to the channel, okay, and remember to press the bell button so that whenever I upload the video, you get the notification also. Okay, if not, bye bye.